In the next two video lectures, we will look at techniques which try and investigate what networks have learnt post hoc. This includes both feature attribution or saliency-based methods which attempt to identify which parts of an image are most crucial to a prediction, and visualization methods which specifically try and engineer images which maximize the activation of individual units in the network. In this video, we'll start by looking at the saliency mapping techniques. The simplest example of these, which is somewhat computationally intensive but nonetheless effective, is occlusion. This works by graying out patches of pixels from an image and then passing the image through the prediction to see how this impacts the prediction probabilities. A heat map may then be generated by doing this at different locations in the image and then filling the output map with the probabilities at each pixel. The probabilities will be lowest for patches centered over the most important parts of the image. For example, here, the dog's faces and the car's wheels. In the same paper which first proposed occlusion, they also proposed a different approach which sought to backpropagate activations from some neuron in the network back to the input space. In this way, you do more than just see the low-resolution activation map, you track backwards through the network to see where these signals originated from in the image. They called this approach deconvNet. The basic idea here is to use the same components of a standard CNN, convolution, activation and pooling, but in reverse. Thus, starting with the activations coming in from a previous layer, first unpool, in other words, project incoming signals back to the locations which were found to be maximal during the forward pool. This requires the algorithm to save a mask which stores these max locations, or switch locations as they call them, as they're learnt during forward pooling, so as to then apply them during backwards or unpooling. After this stage, the signal is rectified, in other words, passed through a ReLU to keep signals corresponding only to positive gradients. And then finally, the signal is passed backwards through convolutional operations by transposing the filters. When these operations are tracked backwards from a single neuron, singled out from a layer by zeroing out all the other activations or channels for that layer, then these are the types of maps which result. So in each case here, 9 visualizations are shown for each neuron, each projected back to pixel space, and then shown alongside the corresponding image patches which generated them. Where actually for layer 1, there are 9 image examples for each feature, whereas in all the other layers the relationship is 1-to-1. These show that early layers act as edge detectors. Intermediate layers seem to be detecting more complex textures, and later layers detect whole objects, noting that the features themselves are tuned only to focus on very specific content from an image patch. For example, here, for layer 5, row 1, column 2, the images themselves seem to be all very different, but the feature itself appears to be focusing on the grass. The authors of the deconvNet paper also did experiments on the evolution of these features during training and noticed that while lower layers appeared to converge after only a few epochs, higher layers needed more training. They also ran experiments while translating, rotating and scaling the input images and noted that while this had a dramatic impact on the earlier layers of the network, impact was much reduced at higher layers for translations and scales. So here you see some examples of transformed images for each of translation, scale and rotation. And then in the second and third column, a plot showing the Euclidean distances between the feature vector encoding of these representations for both the transformed and the original images for layer 1 and layer 7. So you can see the distances are much bigger for layer 1, but much reduced for layer 7, and this has the impact that when it comes to the final prediction accuracies, small translations and scales have almost no effect. On the other hand, without specifically being tended to through augmentation, networks are not built to model rotations, so any amount of rotation just causes the prediction probability to drop off completely. So next after deconvNet came guided backprop. So this was essentially an adaptation of the deconvNet to work with strided convolutional networks instead of networks with max pools. It works by modifying the reverse pass through the ReLU to combine both the results of a deconvNet style inverse ReLU operation, which sets negative values from the reverse operation to 0, with the masking being implemented using a standard backwards pass through a ReLU, which actually corresponds to the result of this f is greater than 0, or following the notation from our original networks, z is greater than 0 operation, where f here refers to the result of the linear convolutional operation, and f is greater than 0 is therefore the gradient of the ReLU. So when you're backpropagating through a ReLU, you just do an element-wise multiplication with this mask, which equates to this mask. The problem with this mask is that when you backpropagate through this mask, it is corresponding to the negative values of the forward operation, and so negative values from the backwards operation get through. Whereas the reverse ReLU of the deconvNet is specifically designed to get rid of these negative partials coming through from the layer above, and then guided backprop just combines both of these approaches together. As a result, feature visualizations for guided backpropagation are qualitatively very similar to the ones that we saw for deconvNet. The authors do argue that their method is better at visualizing higher layers in the network. However, this specific comparison with deconvNet is applied for a network which is trained with strided convolutions, and then the max pools are implemented for the deconvNet after training, so it's quite artificial and not a straight comparison. But the main point they were trying to make in the paper was actually to argue for the use of strided convolutions within what they call an all-convolutional net. And so this is just the point that they wanted to make. Next up is Grad-cam. So this produces rather different visualizations to the two previous methods, instead much more closely resembling occlusion maps. In fact, the authors imply that the method itself is rather like estimating a one-shot occlusion map with a single pass through the network. Grad-cam works by isolating the gradient of a specific class score, here termed YC, with respect to the feature map activations from a given convolutional layer, which in their notation is AK. These activations undergo global average pooling to return one importance value over all space for each activation in that layer. So in other words, they return a channel or neuron importance score for that class. The final Grad-cam map is then generated as a weighted average, multiplying each activation map with its importance score for the class, and then summing over all activations, and finally passing through a ReLU to suppress negative gradients. This is because negative gradients can be seen as just highlighting the regions which actively act against a class prediction, in other words, indicating image features that are definitely not belonging to that class, and thus are more likely to relate to another class, basically just making them a distraction. And so as a result of these choices, the approach generates a more coarse, because it's really backpropagating signals purely from the final output neuron, which has a very large receptive field size. However, the outputs are more discriminative and more focused, arguably, than guided backprop, which picks up on many different things from the image and occasionally more than one object. And in this way, the maps are qualitatively similar to occlusion whilst being orders of magnitude cheaper to compute. And in this way, the authors were able to show evidence that the approach could be used to diagnose or investigate classifications of adversarial examples, for example, where when there are no adversarial examples or noise added to the image, the Grad-cam map is quite focused and makes a lot of sense, whereas when adversarial noise is added, which changes the classification to something completely different, the areas of the image that are being focused on are clearly not specific to any of the important objects in the image. And they also used it as a means of diagnosing other failure modes. For example, in this case, the picture was predicted as a snake, and you can see from the heat map why that might be the case, because it's just focusing on a green part of this coil. So finally, let's look at layer-wise relevance propagation, or LRP. So this takes a similar approach to Grad-cam, but instead seeks to conserve the flow of importance as it tracks backwards from one layer to the next. Thus, the relevance in layer J, which is immediately prior to layer K, is estimated as a weighted sum of relevance from all the neurons in layer K, where here Z is a linear sum of activations A for layer J and weights W for layer K. So this corresponds to the convolutional operation. And this AJWJK essentially is summarizing the extent to which that neuron J has contributed to make neuron K relevant. Specifically, a high WJK would mean that a high weight was being assigned to the contribution of activation J when estimating the output of neuron K. And then the sum over all J in the denominator acts to enforce conservation of total amplitude as the activations are traced back through the network to the input space, such that at each consecutive layer, the total sum of relevance of these activations is conserved, such that in the end, this will mean that the relative amplitude of the gradients, when they get projected back onto the input image pixel domain, will be interpretable as indicating the relative importance of different features in the image to the prediction. However, as we have repeatedly seen, the loss landscape of a deep network can be extremely noisy. So there are variants of LRP to address this. For example, this one adds a small perturbation of epsilon in the denominator, which acts to suppress the contribution of weak activations, such that if all contributions of J to some neuron K are weak or contradictory, returning a low overall sum, the epsilon will raise the denominator slightly to reduce how much these signals get boosted in the output. As a result, the maps should get sparser and therefore focus more on the most salient features. At the same time, it's also possible to tune the relative trade-off of positive and negative gradients using the gamma rule, where the higher the gamma is raised, the more negative contributions will be suppressed. So tuning this can help deliver a more stable explanation. So we can see the different types of explanation offered by each approach in the top row here, where it's clear that this basic form LRP0 is generating really quite noisy predictions, whereas LRP epsilon is most denoised and very specific, but arguably too sparse to interpret. On the other hand, the LRP gamma is just looking at the positive contributions and amplifying these. So you can quite clearly see structure in the image, but it's also quite prone to picking up spurious variations like this lamppost, which shouldn't be necessary for classification of the desired output label, which is this castle. So for these reasons, the author suggests that a composite approach might be preferable, which combines predictions from all three types of LRP, where in this paper they specifically suggest that you run different types of LRP for different layers of the network. And to finish, here are a couple of examples of the use of saliency mapping techniques for interpretation of medical CNNs. So in this example from 2016, Christian Baumgartner proposed a modified version of guided backpropagation to support real-time scan plane detection and localization in fetal ultrasound, where here the network is designed to have as many channels at this last convolutional layer as classes, where classes represent the number of planes that need to be detected. So this makes each of the activation maps in this last layer a feature map specific to a plane. And so in contradiction to standard guided backpropagation, the method then makes use of this spatial encoding of the feature maps in order to backpropagate only the 10% strongest activations to generate arguably more focused saliency maps. And in this example, LRP is used for interpretation of regions most attended to for a CNN trained to predict whether an MRI scan belongs to an Alzheimer's class or a healthy control. So as you can see, the prediction is fairly high resolution and discriminative and focuses on areas of the brain known to be impacted by Alzheimer's disease, such as the hippocampus, amygdala, and medial temporal lobe, all of which are associated with memory. They also use the method to interpret model failures, for example, what was driving false positive predictions by the network. So, in summary, saliency-based approaches for model interpretation seek to generate heat maps which highlight which areas of an image are most important to a prediction. They are applied post hoc and so don't require any specific design of network, and with the exception of occlusion are tracking the backwards throw of gradients through the network to find which features of the image contributed the highest weight to the prediction. By contrast, occlusion simply works by investigating what happens to the prediction when parts of the image are removed, and so it can be a rather computationally heavy but still effective approach. So that completes the video material for this session. Please complete the Keats quiz before going on to the first tutorial for this week.